que estoy. Hola, Carlos.
Hola, Gustavo.
¿Cómo estás?
Muy bien.
Muchas gracias por aceptar.
Es un placer. ¿Empiezo?
No creo que te tengo que presentar, pero
Ok.
no sé si hay un maestro de ceremonias o soy yo.
Usted, doctor Brusual, por favor, adelante con la presentación.
Ok. Buenas tardes a todos. Somos muy afortunados en tener hoy a Carlos Frenk como invitado de la Sociedad Mexicana de Física en la División de Astrofísica para dar esta charla invitada. El doctor Frenk, que es mexicano-británico, tiene un currículum de investigador bastante impresionante. Es fundador de un instituto muy prestigioso en Gran Bretaña, que es el Instituto para Cosmología Computacional en la Universidad de Durham, que fue fundador en el año 2001 y director hasta principios de este año. Es uno de los creadores de la teoría Cold Dark Matter o materia oscura fría, de la cual nos va a hablar hoy. Tiene muchísimos colaboradores, tiene más de 500 trabajos científicos con más de 90.000 citas, tiene un índice H de 140 y tantos, que ustedes saben lo que eso quiere decir, lo difícil que es llegar allí. Y su hobby es hacer modelos del universo, de cómo evolucionó desde que se formó hasta ahora utilizando supercomputadoras, o sea, haciendo modelos numéricos del universo. Es miembro de muchas sociedades, como la Sociedad Real, ha recibido muchas medallas, medalla dorada de la Royal Astronomical Society, la medalla Max Born de la Sociedad de Física Alemana, el premio de Cosmología Gruber, la medalla Hoyle, el premio George Darwin, el premio Humboldt o la beca Humboldt, profesor Oort y muchos otros. También es comendador o comandante del Imperio Británico a partir de 2017. No sabemos bien qué quiere decir eso. Luego es un asiduo presentador de programas de radio y televisión explicando la importancia de su investigación y es una persona ya muy reconocida en Inglaterra, quizás uno de los 5 científicos más citados allá y probablemente de los mexicanos más citados también, si no el más citado. Entre sus logros ha conseguido grandes cantidades de apoyo económico para la Universidad de Durham y unos edificios maravillosos donde funciona su instituto, donde buscó un arquitecto de primera línea como Daniel Libeskind para diseñar el último de estos edificios. Bueno, los dejo con Carlos para que nos hable del modelo de materia oscura fría, la situación actual, los problemas que puede tener, si él ve algún problema, probablemente no, pero ya nos convencerá. Muchas gracias, Carlos, por haber aceptado la invitación.
Pues muchísimas gracias, Gustavo, antes que nada por la invitación y por esta introducción tan generosa. Mi presentación va a ser en inglés, pero porque creo que hay gente, no todo el mundo habla español. Pero antes que nada, quiero saludar a todos mis paisanos mexicanos y me da mucho gusto poder participar en este congreso que marca 70 años de la creación de la Sociedad Mexicana de Física. Bueno, ahora cambio entonces a inglés y okay. So I have to change language, which is always difficult for me, but let me try. Right, so I'm going to talk indeed as Gustavo introduced about cold dark matter, and what I'm going to focus on is how we can test this model in a conclusive way and either rule the model out or rule all alternatives or all interesting alternatives out. So that is the theme of today's lecture. Now, I appreciate that not everybody works on cold dark matter, so let me begin at the very beginning. So the lambda CDM model of cosmogony is a model's quite old. It's proposed in the 1980s, and it's an ab initio model fully specified of cosmic evolution and the formation of cosmic structure. Because it's fully specified, it has very strong predictive power, and therefore, in principle, it can be ruled out. And there have already been many opportunities in the past to rule it out, but it has not been ruled out so far. In fact, it has made a number of predictions that were subsequently verified empirically. For example, regarding the microwave background radiation, large-scale structure, galaxy formation. I'm going to say a little bit more about that in a minute and show you the evidence. In fact, this model has been so successful that it has already earned 3 Nobel Prizes in physics since 2006, including last year's Nobel Prize. So let me describe in one single slide what this model is about. The story begins very soon after the Big Bang, very soon after the beginning of the universe, when the idea is that very early on, the universe underwent a phase of very rapid expansion known as cosmic inflation at an age of about 10 to the minus 35 seconds, driven by the presence of some quantum field. Now, this quantum field was not in the true vacuum, and when it decayed to the true vacuum, that caused the universe to expand exponentially. Now, because it is driven by a quantum field, of course, there are quantum fluctuations. And as the universe expands, these quantum fluctuations are stretched, and they end up becoming genuine classical perturbations in the energy density of the universe. And the pretty incredible proposition of modern cosmology is that all structure in the universe, galaxies, galaxy clusters, and so on, they all come ultimately from these quantum fluctuations during imposed in the universe during inflation. And these fluctuations grow essentially by gravitational instability, which is driven by dark matter. And in the lambda CDM model, the dark matter is a cold particle. I'll tell you in a minute what that means, produced at some very early time. It's some elementary particle different from the ordinary matter that makes up baryons, of which we are made. Now, so the and stars and so on. So this dark matter then amplifies these small perturbations. They grow during the Big Bang era. And the first opportunity we have to test these ideas is 350,000 years after the Big Bang, when the first atoms form and the radiation of the Big Bang is free to escape, producing the cosmic microwave background. So imprinted in the cosmic microwave background should be evidence for these processes that I'm talking about. And I'll come back to that in a minute. Now, the idea that the dark matter might be some form of elementary particle, non-baryonic, that is distinct from baryons, was already proposed in the early 1980s, and it was immediately realized that one can, from the point of view of cosmology, classify any particle of any kind or any mass into one of 3 families, known as hot, warm, or cold dark matter. The best example of a hot particle would be a neutrino with a small mass of a few tens of electron volts. At the other end, there's cold dark matter, and here there's some uncertainty about the mass of the particle. And you see in a minute they behave exactly the same from the point of view of cosmology. Could be an axion or could be a supersymmetric particle or neutralino. In the 1980s, there were no candidates for the intermediate case of warm dark matter, but now we have a very interesting candidate called a sterile neutrino with a mass, say, of a few kilo electron volts. Now, the reason for the names and the reason for the simplification is encapsulated in this diagram. So what's plotted here is the power spectrum of these quantum fluctuations, if you like. That's the power as a function of spatial frequency, large scales are over here at small k, and small scales are here at large k. Now, inflation is a scale-free process, so it predicts a spectrum of density perturbations, which is just the power law, as shown here. But as the universe expands, then these fluctuations can be damped or they can grow. For example, if the dark matter is a hot particle, say a neutrino with a mass of a few tenths of electron volts, these particles are relativistic at early times. So they essentially moving too fast to be contained in perturbations of small wavelength. And so they essentially free stream out of all fluctuations smaller than the size of a galaxy cluster. And so in the case of hot dark matter, the power spectrum acquires a cutoff that you can see here on the scale of galaxy clusters. In the case of cold dark matter, there is also a cutoff, but these particles are very cold. So they are, in the case of the axion, they are never relativistic, they're never even in equilibrium. In the case of neutralinos, they are in equilibrium only for a very brief period of time. And there is a cutoff, but the cutoff is on the scale of the Earth. And I will come back, in fact, to this Earth mass dark matter halos in a little while. And the intermediate case is the case of warm dark matter, KeV mass. The cutoff wavelength scales roughly inversely with the mass of the particle. So if the mass is KeV, then the cutoff occurs on a larger K, smaller scale, corresponding to dwarf galaxies. So that's the simplification, and that was recognized in the 1980s. And one of the very exciting things about this subject is that these are very well-defined initial conditions, and they can be tested with astrophysics. So how do we test these ideas? Well, you need to calculate the consequences for structuring the universe of this power spectrum. And the best way to do that is by using the technique of cosmological simulations. So let me tell you briefly what those simulations are about. You start with an assumption about the content of the universe, that the dark matter is cold or hot or whatever, and that completely specifies the initial conditions because we know the power spectrum of the fluctuations, and because they're quantum fluctuations, they are Gaussian distributed. So we know everything about the initial conditions. That's all we need to do then is solve the relevant equations. If we're interested only in the behavior of dark matter, we just need to concern ourselves with the Boltzmann equation and the Poisson equation, and of course the Friedmann equations that describe the expansion of the universe. But if we're interested in more complicated phenomena like gas dynamics, the phenomena that give rise to stars and galaxies, then the problem becomes a lot more complicated, and you need to contend with radiative hydrodynamics and what we call subgrid astrophysics. And I will come back later briefly to tell you how there's been a real breakthrough in this part of the problem in the last 5 years or so. But the easy part is to follow the evolution of the dark matter. You just need to solve these equations, and there are many techniques to do that. So you apply those techniques in a large computer, and then you go and see what comes out at the other end. So it's a very well-defined, very well-specified problem in computational physics that we know how to solve. Now, the first hypothesis to try was, of course, the neutrino, because at least we know the neutrino exists. And in 1981, maybe perhaps some members of the audience might remember this, if you have gray hair like I do, that across the Iron Curtain came this rumor that five Soviet astronomers led by Vladimir Lyubimov had actually measured a neutrino mass of exactly 30 electron volts, which was immensely exciting, because that's exactly, we know how many neutrinos there are in the universe, and if each of them weighs 30 electron volts, that would provide exactly the density required for the universe to be closed. And so that was very exciting, and the first candidate to try was, of course, that one. Now, unfortunately, the joy didn't last very long, because it was soon realized that a universe dominated by neutrinos produced a galaxy distribution that didn't look at all like the real galaxy distribution that we knew about in the 1980s. And that's because the cutoff in the power spectrum is at such a large wavelength, that wavelength of corresponding to galaxy clusters, that the galaxy distribution in a neutrino universe would end up with these very large structures that have no counterpart in the observed universe. So that was a shame, but it was the first result from this program, the realization that Lyubimov's experiment had to be wrong, that the neutrinos could not make an appreciable contribution to omega, and therefore that the mass had to be much smaller than 30 electron volts. The next thing to try was CDM, and these were the first simulations of what is now known as lambda CDM. Now, you might wonder why in 1985 we were thinking about the cosmological constant. I can tell you about that next time I have the pleasure to go to my native country, Mexico. And if some of you invite me to a bar, I can tell you all about why in 1985 we were already thinking about the cosmological constant. But the main result here is that the lambda CDM universe looked a lot more like the real universe than, say, a neutrino universe. So that encouraged further research into this sort of slightly, well, not slightly, more than slightly, very bizarre assumption that structure in the universe came out of quantum fluctuations amplified by some mysterious non-baryonic elementary particle. Now, but the real breakthrough, I think, came from studying the microwave background radiation, which, as I said before, gives us an opportunity to test these ideas directly. So it was predicted, I'll tell you in a minute by whom, in the 1980s, that these quantum fluctuations, of course, affect the energy density of the universe, but they also affect the temperature of these radiation. So there was a prediction made that the temperature of the radiation should not be uniform, but should have a very characteristic pattern of hot and cold spots, directly reflecting the nature of these quantum fluctuations. It suffices to say that the author of that prediction was Jim Peebles in 1982. Here's a picture from a plot from from his paper, where he calculated what these temperature power spectrum. This is the power spectrum again, but now projected on the sky, and of the temperature of the radiation, not the energy density as we had before. So is the power spectrum, again, large scales here, small scales there, as a function of separation on the sky, or multiple L. And what you can see here is that the temperature structure of this microwave background is complicated. It has all sorts of features. They relate to coherent oscillations of the photon baryon fluid in the early universe, but it was perfectly well understood and calculated in great detail by Jim Peebles, who, of course, as many of you will know, finally won the Nobel Prize in physics last year. He should have had it before, more than once, because his contribution to cosmology is just enormous. So Jim is a true giant, and not just one of the most brilliant physicists that I know, but also one of the finest individuals that I had the luck to meet in my life. And he's the mentor of my generation of cosmologists and many other generations after us. So Jim made those predictions. And then the temperature of the microwave background was measured in detail in 1992, 10 years after Jim's paper by the COBE satellite, which showed that the pattern of the temperature structure, which is what you see here on projection on the sky, is not uniform. It has hot and cold spots. And this discovery of the temperature structure of the microwave background radiation earned George Moore the Nobel Prize in Physics in 2006. This temperature structure was remeasured 10 years later by the WMAP satellite, and then 10 years later again by the Planck satellite, with much improved resolution and sensitivity. So here is the plot of the temperature of the microwave background as measured by Planck. The red points are hot spots, the blue are cold spots. And what you're seeing here, if the theory is correct, is nothing else than these amplified quantum fluctuations from inflation. So that's what we're looking at when we look at this pattern of hot and cold spots. Now the lambda CDM model, this is the quantitative comparison and between Jim's Peebles, these calculations, theoretical predictions in green compared to the measurements in red. I'm sure everybody in this audience has seen this plot, and I hope everybody has been as marveled by this as cosmologists are, because this really is a tremendous triumph of modern, not just cosmology, but I think of modern physics. I should mention that measuring these fluctuations is not easy because they're very, very small in amplitude. So these fluctuations represent just deviations from uniformity of only 1 part in 100,000. So it's a truly heroic effort both to predict the fluctuations and then to measure them at the sensitivity required. Now, lambda CDM has 6 free parameters which can be fit by comparing with the data. And some of these parameters are, in fact, physical parameters. So, for example, this is the density of baryons, which we now know with a precision of 1%. So there's 3 decimal points here, only 1 there. So we know the density of baryons in the universe to a precision of 1%. And similarly, we know the density of cold dark matter also to a precision of 1% or so. And just comparing these 2 numbers here, you can see that this number is a lot bigger than that one, and the errors are very small. And so what we have here, just from the microwave background radiation, is a 40 sigma detection of the existence of these exotic non-baryonic elementary particles that make the dark matter. So these are another remarkable result. We can infer that the dark matter has to be an elementary particle just from looking at signals that were emitted when the universe was 1,000 times smaller than it is today. Now, this object has advanced enormously from these simulations from the 1980s with 32,768 particles from there, and simulations of dark matter halos, as you see here, just with a few thousand particles. So the Milky Way would form in a halo like this. So the subject has increased enormously, advanced enormously, increasing quality and precision and size. And today we have a complete description of the distribution and properties of the dark matter under the assumption that it is cold dark matter. So I think one can regard this problem as a solved problem. So the problem of what is the distribution of dark matter on all scales, what is the structure of dark matter halos, this is, at least in a dark matter only universe, it's a problem that is solved. There's not much more to add to it. And that's the result of work by many, many groups, many people around the world, including in Mexico, over the last 40 years or so. Now, at the same time, there's been enormous progress in mapping the galaxy distribution in the real universe. Here's a plot from the Sloan Digital Sky Survey. The CFA survey that I showed earlier had a grand total of 2,148 galaxies measured. The Sloan has well over 1 million redshifts measured, and projects that are just getting on the way now will measure tens of millions of galaxy redshifts in the next 5 to 10 years. So it's been a tremendous program observationally as well. So let me summarize what I've said so far. So here on the right are predictions for the galaxy distribution from simulations, from something called the Millennium Simulation. And these slices are taken to have the same geometry and selection as the slice just opposite. So you can compare this to that one, which is the 2DF Galaxy Redshift Survey, this to that one. And so you can see just by eye that the agreement is very, very good. And of course, you can do all sorts of statistical analysis, the simplest one of which is just the power spectrum that I showed before, shown here, where the microwave background power spectrum is extrapolated to redshift 0 using linear theory, where you can compare it directly with the power spectrum measured in the galaxy distribution. And lambda CDM is the curve here in black. And as you can see, the agreement is pretty amazing. And in fact, these error bars have shrunk a lot. This is a plot I got from Ariel Sanchez 15 years ago. I ought to update this plot because the error bars here are now a lot smaller. Now, so let me then summarize. So far, the lambda CDM model was proposed in the 1980s, is now empirically supported by observations of the temperature of the microwave background at redshift 1,000, and then again by comparison with observations of the pattern of galaxy clustering in the universe today. And so this is a pretty good, great success of the theory. But if you stand back for a second and say, well, this is really good, but what have we learned about the real universe? Well, this agreement doesn't tell us anything about lambda. Lambda is the cosmological constant. We know nothing about it. And in fact, if you try to predict from first principles what the value should be, you get the wrong answer by a mere factor of 10 to the 137. So the cosmological constant that you would predict from simple arguments in physics bears no resemblance to the one that we see in the universe. So this agreement doesn't tell us anything about lambda, but it doesn't even tell us that the dark matter is called dark matter, because, for example, if the dark matter was a warm particle, as we saw before, the power spectrum looks just the same as CDM, except on scales smaller than dwarf galaxies, where there is this cutoff. But on scales larger than dwarf galaxies are not sampled by any of these data, and then all the success of CDM is transferred directly to the case of warm dark matter. But of course, from the point of view of particle physics, it makes a huge difference whether the dark matter is an axion or whether it is a sterile neutrino. But we wouldn't know from these astrophysical probes. Now, just a word about sterile neutrinos. I don't know if I'm sure that particle physicists in the audience, and they don't seem to be in great favor amongst particle physicists for reasons I don't fully understand, because they're very attractive particles from a number of considerations. For example, not only would they provide a candidate for the dark matter, but also they solve two big problems in cosmology, while in physics. One is, why does a neutrino have a mass? That can be explained, for example, if there are three sterile neutrinos, two of GeV mass, they solve this problem. And they also solve the problem of why is the universe made of matter and not of equal amounts of matter and antimatter. What is known as baryogenesis is also naturally explained if sterile neutrinos exist. And then there should be a smaller mass particle to provide the dark matter. So sterile neutrinos are interesting particles. I'm not saying that's the answer, but they're certainly worth considering. Now, so many of you will be aware that there are claims out there in the world that both CDM and warm dark matter have been discovered. Cold dark matter through gamma rays emitted from the center of the Milky Way. So if the cold dark matter is, say, a supersymmetric particle, in particular if it's a Majorana particle, it doesn't need to be supersymmetric, but if it's a Majorana particle, then in this case, the matter and the antimatter are the same thing. So in regions of high density, like the galactic center, then the particles collide, they annihilate, and if the mass of the particle is GeV, then they will annihilate into gamma rays. And there's a claim, I'll show you in a minute, that these gamma rays have already been discovered. Now, likewise, there are claims that the neutrino, sterile neutrino, which doesn't annihilate, but it could decay. And if the mass is keV, then it would decay into X-rays. And there are claims I will show you in a minute that this decay has already been measured in the spectra of galaxies and galaxy clusters. So here is the reported measurement of an excess of gamma rays towards the galactic center. Nobody disputes that these gamma rays are coming from the galactic center. Moreover, they have the spectrum that you would expect from cold dark matter. Annihilation, there's a cutoff at the few GeV mass. So it's exactly what you would expect. Trouble is, the same spectrum is produced by much more mundane objects like pulsars. And so there's a big debate as to whether this excess is produced by annihilating dark matter or by a population of pulsars in the galactic center. So it's controversial. Likewise, the claims that there is a line, here is the discovery line in the spectra of, in this case, 69 galaxy clusters at 3.57 keV. Here, maybe you see it better here. There's also a great debate as to whether this is really the decay of a sterile neutrino or some other phenomenon. So it seems to me it's very unlikely that both of these claims are right. I can't imagine the universe would have measurable amounts of both cold and warm dark matter. Many people in the subject would say, well, it's very unlikely that either of them is right. So that's the situation in terms of trying to discover the dark matter directly. Now, of course, astrophysicists can just sit there patiently waiting for particle physicists, experimental particle physicists, to discover the dark matter. In the meantime, I think, as I will show you in a minute, it turns out that we can go a long way towards identifying the nature of the dark matter with using astrophysical tests. And of course, the key regime of astrophysics that is relevant is the regime of subgalactic scales, dwarf galaxies, and smaller objects. So here's a short video that will show you how these quantum fluctuations are amplified by the gravity, in this case of cold dark matter, to produce a halo like the halo of the Milky Way. So here's the clock ticking in billions of years, and you see these quantum fluctuations being amplified by gravitational instability. The gravity, of course, causes matter to collect into lumps. These lumps become heavier and they attract more matter, which then makes them become even heavier, and so on. That's the way the gravitational instability works. And you can see here, when the universe is less than 1 billion years old, it's already developed this really beautiful small-scale version of something called the cosmic web. And this is all this richness of structure arises purely from quantum fluctuations amplified just by the force of gravity. So bigger lumps are forming here, that these filaments along which lumps travel, they collide, and then they merge together in a process known as hierarchical clustering. Starts with small things, and structure gets bigger and bigger and bigger, and all sorts of really interesting gravitational physics happen. For example, if we look at this object, it's attracted to this big lump, it's going to go straight through the middle, and you see this spray of particles that are ripped apart from this object by the very strong tidal forces in the center of this halo. So here, this object has about 10 to the 11 solar masses, still 10 times smaller than the Milky Way halo. And most of the activity here, we're still very early on, only 4 billion years after the Big Bang. Most of the activity is now pretty much over. So the galaxy will then form inside this dark matter halo as gas gets attracted by the gravity of the dark matter, falls into this potential, then it cools, and then it becomes unstable and fragments into stars. So that's how we think galaxies actually form. Now, so let me just show you, contrast the formation of the Milky Way dark matter halo in cold dark matter with what we would expect if the universe is made of a stellar neutrino with a mass of 7 keV, which would correspond to this 3.5 keV X-ray line. The mass is twice the decay energy, so the mass would be 7 keV. So here on the left is the same movie I showed you before. On the right is a warm dark matter universe. And you see there's already a lot of stuff's going on in the cold dark matter universe. There's quite a lot of structure, and nothing much has happened in warm dark matter. And the reason is, of course, that the power spectrum is cut off on small scales. So these small fluctuations that we see here, which are on scales smaller than dwarf galaxies, they don't exist in warm dark matter. So nothing forms on those scales. But as time goes by, then the bigger scales begin to collapse. The phases of the two simulations are the same. So this object is the same as that one. This one is that one. And so on large scales, the two are very, very similar, but obviously they're extremely different on small scales. CDM has this large number of structure, which warm dark matter does not have. Now, so some of the first simulations actually of warm dark matter were carried out in Mexico by 3 colleagues, Pedro Colin, who sadly died a few years ago, Vladimir Avila Riz, and Octavio Valenzuela, already 20 years ago. And this is some of the first, actually these are the first simulations of galactic halos, contrasting the large number of substructure that forms in a CDM universe with what you expect in different warm dark matter models with different values of the mass, therefore different values of the cutoff. And you can see just by eye that they are extremely different. So that's work from 20 years ago that opened up this whole subject that's been followed by many people across the world, including my own colleagues in my institute. Now, so here's the movie now, 20 years later, almost, not quite, 2012, done by my former student, Mark Global. And here you can see in great splendor the difference between a Milky Way halo in a cold dark matter universe compared to that in a warm dark matter universe. So you should say, if you look at this for the first time, you say, well, surely astronomers must be able to tell us whether the Milky Way lives in a galaxy like this, or in a halo like this, rather, or in a galaxy like that. Unfortunately, it turns out it's not that easy. Let me tell you why in a minute. So this is a plot I'm going to come back to later, because to me it's an amazing plot. because of the number of orders of magnitude in the two axes. So this is something called the mass function of halos. It's just the number of dark matter halos as a function of their mass. And here you can see it's 25 orders of magnitude in mass and about 25 orders of magnitude in number. So this just shows, maybe not surprisingly, that the mass function is more or less a power law. Gravity doesn't have any scales, and there's a cutoff here because the universe is not long enough or not old enough to have made more and bigger objects. So it's from a paper that just appeared in Nature 2 weeks ago. I'm going to come back to that later. I just want to emphasize here that the mass goes from 10 to the 15, which is the mass of a galaxy cluster, all the way to below the mass of the Earth. The mass of the Earth is 10 to the minus 6 in these units. Now, so CDM then predicts a mass function that continues to rise all the way to an Earth mass. And this is a much smaller scale picture by my former student, Saunak Bose. But it shows that in the case of warm dark matter, as you can see by eye, there aren't any small structures. So the mass function has a cutoff. And characteristically for a neutrino, stellar neutrino of mass 7 keV, the cutoff is on a scale of about 10 to the 8 solar masses. Here, the abundance has dropped by a factor of 10 relative to CDM. That's what you can see here by eye. So the challenge now is, how do astronomers attempt to measure this difference between these two very strikingly different predictions for the mass function of dark matter halos in CDM versus warm dark matter? Now, there are two ways to do that. One, which seems fairly obvious, is just count how many dark matter halos there are, try to measure the halo mass function, and you can count them in various ways. One, which I will talk about in a minute, and then you can just count them if you could detect this annihilation or decay radiation. So let me tell you first about how far we can get trying to count dark matter halos. Of course, naturally, astronomers would say, well, let me count them by counting the number of small galaxies that I can see. Now, so let's begin by counting what we can see. Well, the Milky Way has about 55 satellite galaxies. These are the smallest dwarf galaxies that we can see. We can only see them relatively nearby because they're very faint. And there's 55 of them known. And they have nice names like the Large and Small Magellanic Cloud, Dracos, Sculptor, Fornax, and so on. There's 55 of those known. That's not all there is, because only a certain part of the sky has been surveyed and only to some depth, but it's not difficult to extrapolate. And this was done by my student, Oliver Newton, not Isaac, but Oliver, and where he concluded, just extrapolating from the data that we can see, that the Milky Way in total would have about 125 satellites brighter than the smallest, than the faintest that we can see, corresponding to magnitude 0. So for the physicists in the audience, these are bright, these are faint. Now, why astronomers why they use a logarithmic scale? Well, that's natural. The eye responds logarithmically, but why are the bright things, the small numbers, and the faint things, the big numbers? Ask some astronomer. But these are faint and these are bright, and there's about 125 or so, even though only 55 have been discovered. Now, this is the halo of the Milky Way as predicted by CDM, where you don't need to count. You can immediately see that there's a lot more than 125 dark matter halos here. There's in fact hundreds of thousands of them. So does that mean that CDM is wrong because we only see 50 satellites? We know there's about 100 when the number of halos is much, much larger. Well, the answer is no. This, by the way, is known erroneously, in my mind, as something called the missing satellites problem. And that is the problem that CDM supposedly predicts many more halos than there are observed satellites. But the main point is that most of these halos never make a galaxy. They're just completely dark. And this is something that's been known, well, for 20 years. And somehow people keep coming back to talk about this missing satellites problem. So let me just make one of the first points I want to make is this missing satellites problem. It's a complete misconception. And it's a problem of not understanding galaxy formation, not a problem of CDM. So I'm going to give you a very brief 2-minute premiere on galaxy formation for those of you who are not astronomers. So here's a cartoon. Here's the Big Bang. Here is the epoch of recombination. And when the universe comes out of recombination, well, the hydrogen gas is by definition neutral. That's what recombination means. So there's nothing here. The first small halos begin to form around here, but they're very small, and they cannot allow for this neutral hydrogen to cool, because neutral hydrogen is very difficult to cool, and it only cools from molecules, but gas doesn't cool into these dark matter halos. So this universe is completely dark here. It's called the dark ages. But gradually, bigger and bigger halos begin to form, and then molecules allow some of these gas to cool, and the first galaxies then form in halos of mass 10 to the 7, 10 to the 8 solar masses. Now, these first galaxies, and even the first stars as well, they produce copious amounts of UV radiation. And the UV radiation ionizes the neutral hydrogen, and because around here, the halos aren't big enough, the gas gets heated as it's reionized to 10 to the 4 Kelvin, and the halos that are around here don't have potential wells deep enough. They're still very small mass, as we saw in the movie that I showed you earlier. They are not, potential wells are not deep enough for gas to be able to cool because it's being heated up to this high temperature. Eventually, however, if you wait long enough, bigger and bigger halos should form. It's hierarchical clustering. Eventually, big enough halos will form that allow this gas to cool, and finally, galaxy formation starts again. So there's a phase 1 of galaxy formation. There's an interruption here when the gas is too hot, and then there's a phase 2 of galaxy formation. Now, these are not complicated physics. If you're interested in more details, there's a paper that by my postdoc, Alejandro Benitez Lambay, that came out a couple of months ago. And essentially, before reionization, for gas to be able to cool, then the halos have to be bigger than some critical mass, shown here as function of redshift in orange. So for a galaxy to be able to cool, the halo has to be larger, of mass larger than this critical mass. Reionization occurs about redshift 8. So in here, only halos above this mass can form a galaxy. Reionization then heats up the gas, and then you move to another critical mass, which is a bit bigger. And in order for galaxies to form, the halo now has to be above this particular critical mass. So that's the two critical masses that determine where galaxies can form and where they cannot form. And now, so the main point I want to make with this is this plot that shows the fraction of dark matter halos that can host a galaxy, as opposed to being completely dark as a function of the mass of the halo today. And what you can see here is that all halos with mass less than a few times 10 to the 8 solar masses are completely dark. Fraction of halos with the galaxy is 0. So all these are just totally dark. Above 10 to the 10, say, they're all bright. They all have a galaxy. And then there's this very steep transition between darkness and between light. So, and that's very well understood, simple physics. We compare our simple analytic calculations with simulations and all sorts of other things. This is a robust result. Now, so this is a mass function of halos, and what this tells us is that only this little bit in here of mass greater than 10 to the 10 solar masses or so makes a galaxy. Only these ones make a galaxy. So when we look at satellites, we're only sampling this part. These are all completely dark. We cannot see them with telescopes. And if I say this has been known for a long time, so my former student Andrew Benson in 2002 did very similar calculations and computed the satellite luminosity function, shown here in red, shown here in black, with lots of scattered here at the bright end, compared to the observations that existed in 2002. Only 10 satellites were known, 45 have been discovered since then. And Andrew actually predicted that there should be a population of ultra-faint satellites, which was subsequently discovered by the Sloan Digital Sky Survey. So these are well understood physics. Now we can now attempt or tackle the same problem now using not just analytical simple models, but full powered hydrodynamics cosmological simulations. As I said before, it's really been a breakthrough in this subject in the last 5 years or so by various groups. I'll just show you here a plot from the group that I'm a part of called the Virgo Consortium. There are others, other groups that have achieved similar results. Now here is what we call the local group of galaxies, the Milky Way and the Andromeda galaxy. This is what they would look like if we were able to see dark matter. The universe would be teeming with little halos. It's just such a shame that our eyes are not tuned to dark matter. All we can see with our telescopes is this, only the few lucky big enough halos that manage to make a galaxy. So that's what the local group looks like in dark matter glasses. This is what it looks like through our telescopes. And of course, the quantitative results agree with the simple physical arguments. Here's a plot from Til Zavala showing many dark matter halos, far fewer satellites, and the simulations shown here in green agree perfectly well with the observational data. So this is good. We understand the galaxy formation means that that CDM possibly predicts the observed abundance of satellites. There's no such thing as a missing satellite problem in CDM, but we have not made any progress in our attempt to distinguish CDM from warm dark matter. So, but what we have learned one thing, and we have learned that by comparing satellites, things that we can see, we're not going to get very far. So how do we progress then? Well, we have to look at the dark halos. They are the ones that are actually different in the two cases. So rather than counting faint galaxies, let's try to count the number of dark halos, if you like, failed halos that never managed to make a galaxy. Now, there are three ways to do that. I only have time to talk about two of them, but I just mentioned the first way is something called gaps in streams. So as you saw in the movie, when a satellite or a halo falls into another one, it can get tightly stripped. Now, if this object that falls in happens to be a globular cluster, that produces a stream of stars, a tidal stream that's very thin and very cold. And if a stream like that gets intersected by one of these dark substructures that I'm talking about, it would produce a gap. And in principle, one could try to detect dark matter subhalos in the Milky Way like that. I don't have time to go into detail. If somebody has questions, I'll be happy to explain. But let me talk about the two other methods, which are a lot simpler in my mind. And well, gaps in streams is a very good technique, but I think gravitational lensing has huge promise. And then I'm going to talk a bit about annihilation radiation. So let me tell you about seeing in the dark. And astronomers are very good at that because exploiting a phenomenon predicted by Einstein called gravitational lensing. So if you have a source of light that happens to be behind a very massive object, for example, a galaxy cluster, then, and here's the observer, then light rays from the source are deflected by the gravity of this massive object, which is the lens, and then that deflection, of course, produces a distortion in the image of the source. And if the source, the lens, and the observer are well aligned, then we get this amazing phenomenon that nature has produced, these so-called Einstein rings. And that is just when you have perfect alignment, then, well, you use by symmetry, the source will look like a circle on the sky, this Einstein ring. So that's well understood. These Einstein rings have been measured for 30 years or so, for example, with the Hubble Space Telescope. But now imagine that one of these little objects, 10 to the 7 solar mass, 10 to the 8 solar mass, small halo, those we're trying to detect, happens to also be somewhere in the vicinity of a deflected light ray, like here, for example, then of course this object would also produce gravitational lensing. And what it does is that it distorts the image of the Einstein ring. So here you see an example discovered by one of the pioneers in this subject called Simona Veghetti. And here it is, here's an Einstein ring, and here's the distortion produced by an intervening dark matter halo. The only problem with this is that if you can see it by eye, as you can in this case, then it's not interesting because it's too big. So this object here is it has a mass of 3 times 10 to the 10. It's 100 times bigger than the ones we're interested in. We're interested in the dark ones. And you can even see the galaxy there. So these are not interesting from this point of view. They're very interesting for other reasons, but it shows that this technique in principle can help us detect these small substructures. So my student Chuhan He in Durham has been looking, and then other people around the world doing the same kind of thing, at the realistic prospects for detecting these small halos. And here is an image where this is something called a residual, where you have an image. In this case, it's just a theorist image. It's a mock data made from simulations, but then you have the image, and then you subtract the smooth model, and what's left, the residuals, are in principle the signature, sorry, that's the image, these are the residuals, and the residuals here in here is the signal that in this case, a 10 to the 7 solar mass halo was deflected some of the light from the source. Now, so it becomes a very complicated statistical problem to try and extract the signal. It's very, very hard. It's full of systematics. It's really, really tough. But Chuhan and other people assure me that it can be done. Here you can see what we're looking for. So here is something called a convergence map, which is just a map of the projected mass distribution. In the case of a CDM halo, here's its warm dark matter counterpart. Everything is the same in this experiment. These are just mock catalogs from simulations. But you can see here that in principle, there would be a lot more signal in CDM than in warm dark matter. So it's for the lens at redshift 1. Put the lens further away at redshift 2.5, you get even more signal. These are the residuals. And in principle, it should be possible to detect the difference between these two kinds of distributions. And indeed, Chuhan has been working very hard, doing something called forward modeling and applying approximate Bayesian estimation to many, many more catalogs. I don't have time to go into details. The paper will come out as soon as I get a chance to finish it off, which I hope will be this week. I just want to say that it is possible, in principle, to detect if there is a cutoff in the power spectrum by doing this forward modeling. You need quite a lot of objects. In fact, you can calculate how many you do need, and I'll tell you about that in a minute. But the main point is that if warm dark matter is right, then we should find no small halos. There should be 0 10 to the 7 solar mass halos because the mass function is cut off at 10 to the 7. Warm dark matter predicts no halos of that mass at all. So if it is right, you shouldn't find any. And if you find one, you'll rule out warm dark matter. Conversely, if CDM is right, you should find many 10 to the 7 dark matter halos, and we know exactly how many. So this is, I think, a beautiful physics experiment. Again, I'm going to go quickly through this. If you're interested in the detail, it's a paper by Ran Li and collaborators in Beijing. And the main point is that with 100 lenses, in principle, we could detect if the universe is made of warm dark matter, the cutoff. So plotted here is just the number of these perturbations on an Einstein ring. It's a function of the cutoff mass. So if the cutoff mass is 10 to the 8, then with 100 lenses, we should detect it. If the warm dark matter is the right assumption, but if CDM is right, then we should rule out a warm dark matter with very high precision. And of course, if we don't find these halos, then we rule out CDM, right? So if we find no 10 to the 7 solar mass halo, well, that's the end of CDM. Now, so my lensing with current techniques only allows us to see, and being optimistic, maybe halos down to 10 to the 6, 10 to the 7, maybe some masses using interferometry at long wavelengths in the millimeter and the radio, maybe we can see around here, but there's still only a tiny fraction of the mass function. So how can we see this one? Well, the only hope of seeing this part of the mass function is through, if they happen to be made of Majorana particles, through annihilation radiation. So I want to tell you, just to finish off, a little bit about that. I'm something I'm very excited about, because we now know exactly what we should expect. So as I said before, if the dark matter particles are cold dark matter and they're Majorana particles, then they annihilate into standard model particles. And if the masses are right, they would produce gamma rays. Now, the intensity of the annihilation radiation is given by this formula here. And this is a particle physics part of the formula. This is a cross-section for annihilation. This is the astrophysics part. It's an integral over the squared of the density. It's a two-body problem. It's annihilation. And this is what astrophysicists can produce or can deliver in this quest to find annihilation radiation. So we know... Yep.
Carlos, can you finish in about 5 minutes to have some time for questions?
I will finish in 5 minutes. Thank you, Gustavo. Okay. So we've known for a long time that the density profile of dark matter halos can be described by a very simple formula. So here are density profiles of halos all the way from dwarfs to galaxy clusters. And this line here is a very simple equation. If instead of using physical coordinates, you use dimensionless coordinates, that all these profiles collapse into this very simple form, which diverges like 1 over r to small scales, and it goes off like 1 over r cubed. So this is the structure of dark matter halos. We said it's a solved problem. We know exactly what it should be. And we've known this for a long time. It's a universal formula called the NFW profile, which applies not just to CDM, it applies to all cosmological models, regardless of details, regardless of the value of the cosmological parameters and so on. One way to important characteristics, 2 characteristic values in this formula. One is a characteristic density, the other is a characteristic radius, but they are correlated. So, for example, the concentration, which is related to the characteristic radius, is correlated with the mass. So if you give me the mass, 3 times 10 to the 7, I can tell you exactly what the dark matter profile looks like. Anyway, because I'm running out of time, let me skip through this and go to these results that I say came out in Nature only last week or 2 weeks ago. So here is what, this is not from that, this is older work from the Aquarius simulations. So here is what the gamma ray sky would look like in annihilation radiation if this is a source of gamma rays. So the galactic center is, of course, the brightest part. But as we saw before, the galactic center is controversial because there are pulsars and all sorts of other things. So what we need to really pay more attention to is the small halos that are emitting a lot less radiation, but there's no confusion because they're just made of dark matter. Now, as I said before, in CDM, there's a cutoff in the power spectrum on the scale of the Earth. And here are these program of simulations that we just finished. It took us 7 years to be able to do simulations going all the way to the cutoff mass in the power spectrum. So here we had to design special techniques that you can find out in the paper. But here is a big cosmological simulation. That's the scale here. What we did was look at a low density region, resimulated with 100 times more resolution. So now the bigger object you see here, the bigger objects 10 to the 15 solar masses, the bigger objects here are only 10 to the 12. And we keep doing this successively, looking at smaller and smaller regions of lower and lower density, increasing the resolution by a factor of 100 every time. And this is only level 4. Level 5 here, the biggest objects you see here are 10 solar masses. Now they're only 1/10 of a solar mass. And finally, here, the biggest objects that you see here are planet size, Earth size. And you can see how the topology has changed, a fascinating topic for further discussion some other day. The main point is that we now have the ability to measure exactly what these profiles look like, and amazingly, or maybe not amazingly, because gravity is so simple, here's a plot of the slope of the density profile of all these dark matter halos, ranging from the mass of the Earth all the way to the mass of a galaxy cluster, and they all have the slope of the NFW profile, or something called the Anasto profile, slightly more precise. So we now know exactly what the profiles are. We know how the concentration of these halos changes with mass. Therefore, we can calculate the contribution to the annihilation luminosity for the first time precisely, and that's shown in this diagram. So this is the annihilation luminosity per unit logarithmic interval in mass, and you can see that it's more or less constant from about the mass of the Earth, a bit bigger than that, all the way to 10 to the 10 solar masses are all the dark halos, but of course there are many more halos of this mass than of that, and so the luminosity is dominated by these Earth mass halos. And all previous extrapolations, I don't know if including ours, in the audience, there may be people who made this, they're all wrong, sometimes by factors of 1,000 or so, and that's because simulating these Earth mass objects has been a very difficult program. So I'm done. Let me just conclude. Lambda CDM is a great success on large scales, but that doesn't allow us to distinguish CDM from warm dark matter. We have to do that on small scales. And I talked about gravitational lensing, how this can potentially rule out CDM, and then annihilation radiation. I think we now understand what we should expect And just to show you very quickly, I went very fast through this VVVV project. The smallest halos in CDM have an Earth mass. They are well described by the NFW density profile, and these very small subhalos dominate the annihilation luminosity. And so we now have very clear predictions for what the next generation of gamma ray observatories should be looking for. And I am done here, Gustavo. Thank you.
Muchas gracias, Carlos. Tenemos aquí algunas preguntas. Edgar Peralta, ¿me escucha? ¿Puedes hablar?
Sí, sí, escucho, gracias.
Bueno, háganla en español para que sea más rápido.
Ok, está bien. Muchas gracias por la plática. Y quiero preguntar si hay algún límite para los halos de materia oscura pequeños, si existe un límite para la formación de ellos. Y si no lo hay, o sea que puede haber halos de cualquier tamaño, aunque sean muy pequeños, puede haber halos de materia oscura del tamaño, no sé, del Sol, por ejemplo. Y si es así, podemos pensar que están distribuidos en todas partes y por lo tanto podríamos encontrarlos dentro de nuestro sistema solar.
Right, efectivamente. So, let me answer in English. I speak faster in English than in Spanish. So what happens here is the cutoff, if it's called dark matter, whether it's an axion or a supersymmetric particle, there is a cutoff. So this one at the mass of the Earth, there's nothing smaller than that, but that's just for a particular supersymmetric particle, but it's around here. So there is a limit, even in the case of axions, there would also be a cutoff, maybe not at 10 to the minus 6 solar masses, but at some other mass. And then there are halos that form from, say, the Earth, mass of the Earth, to all bigger masses, as I show you in that mass function. Now, could there be some of these in the vicinity of the sun? I think that's a very, very good question, and I don't have the answer for that to that question yet. I think it's very unlikely because most of these halos get disrupted by tidal forces before they get as far in as the sun. But it's just a statistical question. We calculated already before we did the simulations, actually, that there's the dark matter distribution in the solar system should be smooth with 99.9 confidence level, smooth to a level of 1 part in 10 to the 4. But of course, that doesn't exclude that one of these small Earth mass objects could wander into the solar system, and that would clearly be something very interesting. If it hits the Earth, well, it won't do anything to the Earth, but it will completely confuse attempts to discover dark matter in the laboratory. So the answer to your question is yes, there is a limit for a, say, 100 GeV supersymmetric particle is the mass of the Earth, 10 to the minus 6, but that number would change depending on the nature of the dark matter. And could there be small objects in the solar system? Sure, but with very low probability.
Muchas gracias.
Tenemos tiempo solo para una o dos preguntas más porque viene otra charla invitada. Está Luisa Fernanda Cardona Torres.
Buenas tardes, sí. Voy a hacer la pregunta en inglés. Sería, according to the last simulation shown, even the voids will have tendrils of dark matter structure, as you were assuming in the lowest density regions, and still you found low mass dark matter halos.
Yeah, that's absolutely correct. So here you see, so these would be, the biggest objects here would be Milky Ways, and you see these smaller objects are present everywhere. So these are all distributions at different levels of resolution at the present day universe. So even when we go to the Earth mass objects here, then you see that they all exist along these sort of filaments. And so, yeah, they're everywhere. And of course, the only ones that we can see are the ones that fall into the Milky Way halo. They have to be very close by because they have such a small mass that the annihilation radiation would be pretty faint. So we would be able to see. So the way you could detect them is if you suddenly see a source of gamma rays with no stars, no astrophysical object associated with them. And these would be small halos, subhalos inside the halo of the Milky Way, but you should see them everywhere, outside the Milky Way and everywhere in the cosmic web.
Y Octavio Valenzuela, uno de tus colaboradores de hace 20 años, tiene una pregunta.
No, no era colaborador mío, el colaborador de Vladimir y de Pedro.
Okay. Perdón.
pero lo conozco bien. Bueno, lo conocí bien.
¿Estás allí, Octavio?
¿Qué tal? Felicidades por la interesante plática. Nada más quería preguntar, I would like to ask, under which conditions would you consider seriously the possibility that dark matter is composed by two kinds of particles? Maybe cold and warm or cold and hot?
Well, I mean, we already know there is more than one type of dark matter. Well, there's at least 3 types of dark matter. The neutrino doesn't have a mass of 30 electron volts, but we know it has a mass, probably just a fraction of a milli-electron volt. A milli-electron volt masses, but it is dark, right? Neutrinos are dark matter. So we already know there is a particle, non-baryonic, that is dark matter, but it contributes negligibly to the total dark matter budget in the universe. We know other sources of dark matter, which are baryons. I mean, most of the baryons are not in stars, and they too are dark matter. But again, they produce a negligible contribution. So I have no problem with there being more than one form of dark matter. But to have 2, say, or 3 that make similar contributions, that can exclude it. It just seems to me fairly contrived. I mean, it's already difficult enough to buy the idea that dark matter is some exotic particle, and then to have 2 which contribute in a comparable way would be difficult to arrange. So the particle physics would have to be very fine-tuned to ensure that you get the right abundance of the right mass to have more than one dominant form of dark matter. So, but of course it could be the case, and in my view, the simplest, obviously, I'm sure everybody would agree with this, the simplest would be possibilities that there's just one dominant form of dark matter, and maybe many other forms. We already say know of 2 others that just make a very small contribution to the total.
Thank you.
Muchas gracias, Carlos. Ha sido una excelente charla. Estoy seguro que el que quiera hacerte preguntas te podrá escribir directamente por correo electrónico.
Con todo gusto y muchas gracias de nuevo por la invitación, y qué lástima que no pueda estar yo ahí en persona, pero así es la vida en estos momentos.
Esperemos que pronto puedas venir.
Hasta luego. Y eso
Hasta
espero
luego,
yo.
muchas gracias.
Gracias, Gustavo.
Hasta
Bye bye.
luego.